Hi everyone, my name is Tiger Zhang and I'm really excited to explain the solutions this week. Before we get started though, I want to say two things. One, so whenever you're doing a math problem or looking at a solution or just thinking about math, you should always think about how do I get to the solution or how do I approach this problem or this type of problem. Not what is the solution to this problem or whatever. So math is a problem-solving process, and this can really help you in problem solving because you can think about what you want in the solution and stuff like that. Another thing is that in the AMC8 class, which is another class I also explained the solutions to, so once I was explaining a problem and my video game thing just popped up. Yes, I used to play video games, but now I don't because I'm realizing how much time it's wasting me and I really should be doing more important things. Like for example, math, which I'm very passionate about. And I think if you have a passion, then it's going to be easier for you to stop playing that much video games. So that's all I'm going to say. Let's start. Problem 1. A Fibonacci sequence, the curly braces, A subscript n, with n greater than or equal to 1 satisfies that a1 equals a2 equals 1 and an plus 2 equals an plus 1 for n greater than or equal to 1. What is the remainder of a2020 when it is divided by 9? So let's first get the symbols and stuff clear. So this curly bracket thing just denotes sequence. It could be a finite sequence, like A1, A2, A3, or it could be an infinite sequence, A1, A2, A3, and so on. So, is it a finite sequence or an infinite sequence? Well, this n greater than or equal to 1 right here tells you that n can be anything greater than or equal to 1. So it's the bottom choice here. And then this is a recursive sequence. That means there are two parts to it. One part is the base case, and that's very important, but sometimes underrated. So the base case, it's stated here, A1 equals A2 equals 1. And then there's the recursive definition. So it's right here. So what is this? Well, you can plug in any number to n, and then it tells you that this equation must be true. And you can use it to see what the next terms in the recursive sequence are. So let's evaluate some terms. Now, there's 1, A1 equals 1, A2 equals 1, A3 equals, what is A3 equal to? So using the recursive definition, if you plug in n equals 1, then you get A3 equals A1 plus A2. So it's just their sum, which is 2. And then if you plug in n equals 2, then you'll get A4 equals A2 plus A3. So then A4 is again the sum of the previous two terms, which is 3. And then you can see that plugging in bigger n will make it similar. Like A5 is equal to the sum of A4 and A3, the previous terms, which is 5. So you can see the pattern here. So it's 8, and then 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. Then 55 and 89, and then 144. This is getting big. So how are we gonna do anything about it? Well, let's look at what it's asking. What is the remainder of A2020 when it's divided by 9? So whenever you have some really big number that doesn't seem to be that interesting as a number, it's very interesting as a year. But it's not very interesting as a number. Not really. So in these cases, it's almost always a repeating sequence, or it has some pattern, like 1, -1, 2, -2, ... So it says when it's divided by 9. So maybe we can take the remainders of each of them when they're divided by 9. So let's try it. 1, 1, 2, 3, 5, and 8 are all just themselves when divided by 9 and have a remainder. 13, the remainder when 13 is divided by 9 is 13 minus 9, which is 4. And then 21 is 21 minus 18, which is 3. 34 minus 27, which is 7. 55 minus 54, which is 1. 89 minus 81, which is 8. And then 144 is divisible by 9, so it's 0, not 9. It's 0. And then you'll see that even though the remainders when divided by 9, there's still some nice properties, like 4 plus 3 equals 7, or 7 plus 1 equals 8, that are consistent with the original sequence. But the problem is here, what about 8 plus 4? That's not equal to 3. But then remember, we're working in divisibility by 9, or mod 9. So in mod 9, something like 2 would be congruent using 3 equal signs to like 2 plus 9, or it would be congruent to 2 plus 18, or 2 plus 27, and then mod 9. So this one is similar. We just take the mod 9s, and then it will be consistent with the original sequence. Like 8 plus 4 equals 12, and then 12 minus 9 is 3. So that's the 3. Yeah, so let's compute a few more terms, because it's not really very clear when it's going to repeat. Not yet. 8 plus 0 is 8. 0 plus 8 is 8. 8 plus 8 is 16, but then mod 9, that would be subtracting 9, would be 7. And then 8 plus 7 is 15, minus 9 is 6. 7 plus 6 is 13, minus 9 is 4. 6 plus 4 is 10, minus 9 is 1. 4 plus 1 is 5. No minus 9 this time. 1 plus 5 is 6. 5 plus 6 is 11. Minus 9, it would be 2. 6 plus 2 is 8. 2 plus 8 is 10. Minus 9, it will be 1. Then 8 plus 1 is 9, which would be 0. And then let's do a bit more. 1, and then 1, and then 1 plus 1 is 2, and then 1 plus 2 is 3, then 1 plus 2 plus 3 is 5, and then 3 plus 5 is 8. Well, you see that this is exactly the same thing as this. So it got repeated. So there's the repeat. Those 24 get repeated over and over. And you can prove that by just saying that repetition doesn't do anything to the sequence. So every 24 numbers is going to go back to 1. So let's see what is the remainder when 2020 is divided by 24. So let's see. So we subtract. This time it will require some calculation. It's 192. And then that would be 10. And 100 minus 96, that would be 4. We don't need the quotient here. We just need the remainder. So we don't need to write anything there. So the remainder is 4. So what does that mean? That means a to the 2020 is equal to a4, because 2020 divided by 24 has a remainder of 4. So 2020 is equal to something times 24 and then plus 4. And then since if you add 24, subtract 24 from a number, it's still going to be the same, the sequence. So that means A2020 is equal to A4. And then that basically solves our problem. A4, we can just look here, it's 3. So A2020 has a remainder of 3 when it's divided by 9. Okay, so problem 2. What is the product of all real numbers x satisfying 2 times log base 2 of x minus 1 is equal to 1 minus log base 2 of x plus 2? So you see 2 logs and they're the same base. So what you can do is there is a great logarithm property that says log base a, log base, actually let's use n, log base n of x plus log base n of y equals log base n of xy. And similarly, you can use this formula to create another formula. Log base n of x plus log base n of x, that's just 2 times log base n of x, is equal to log base n of x squared, simply because of the formula. And you can just keep doing that, keep adding log n of x, so you can get log n of x cubed. So then k times log n of x is equal to log n of x to the power of k. So that's the formula that we're going to use. So let's start by rearranging this equation so that the negative log 2 of x plus 2 becomes on the other side, goes to the other side. So 2 log base 2 of x minus 1 plus log base 2 of x plus 2 equals 1. And then we use the formula on this, so we get log base 2 of x minus 1 squared. Then plus the rest, log base 2 of x plus 2 equals 1. And then we use the formula again on those two to get log base 2 of x minus 1 squared times x plus 2. That's equal to 1. So by the definition of logs, 2 to the 1 is equal to x minus 1 squared times x plus 2. So the left-hand side is just 2. Then the right-hand side, we can simplify this a bit. So first, the square becomes x squared minus 2x plus 1. and then you multiply that with x plus 2 to get, let's multiply each term, x squared with the x cubed. And then negative 2x with the x minus 2x squared, and 1 with the x plus x. And then x squared with the 2 plus 2x squared. Then negative 2x plus 2 with the 2 minus 4x and 1 with the 2 plus 2. So we know that 2 is equal to that. So there's a cancellation with this 2 and that 2, and then there's another cancellation with this negative 2x squared and the 2x squared. So this I'm just going to erase it. This becomes 0. And then the x minus 4x is just minus 3x. So x cubed minus 3x. And then there are 2 solutions. There are 3 solutions actually. But we'll see that not all 3 of them work. So x cubed minus 3x is equal to x times x squared minus 3, which is equal to x times x minus root 3 times x plus root 3. Just simply because the roots of x squared minus 3 are positive and negative root 3. So this is trying to say that the values of x which make this equation true are 0, negative 3, and negative root 3 and root 3. But if you look up here, not all of them work. Why? Let's try 0. 2 log base 2 of 0 minus 1, that's negative 1. Wait a minute. This isn't defined. So we should get rid of that. 0 is not a root. Let's erase this. Then negative 3, let's try that one. 2 log 2, negative root 3 minus 1 equal 2. Wait a minute, this is another negative. So this isn't defined. Let's cross that out. And then the only other one is root 3. So let's see if it works. 2 log base 2 of root 3 minus 1 equals 1 minus log base 2 of root 3 plus 2. So there doesn't seem to be any negatives here on the logs. And I'm not gonna do it right now, but if you calculate it, you'll see that this actually does work. So yeah, there's a lot of square roots and division and squaring and stuff, but once you do the calculation, you'll see that it works. So the only solution is x equals root 3. Problem 3. A lucky number is a positive integer which is 19 times the sum of its digits. How many different lucky numbers are there? So if you start looking at this problem for some time, you'll see that this problem is kind of unorderly. What do I mean by that? There's no restrictions on the number of digits, and digits are a big part of this problem. So let's put some restrictions on the number of digits. Could it be a 1-digit number? No, the sum of its digits of a 1-digit number is just itself, and that one-digit number can't be 19 times itself. How about two-digit? Well, let's see. The positive integer is 19 times the sum of its digits. So let's try all the multiples of 19. 19, so we have 19, then 38, then 57, 76, 95. You can tell at like a quick glance that these don't really work. So these 5 numbers are the sum of the digits, and that times 19 is way more than a 2-digit number. So that won't work. It turns out a 3-digit number will work. So yeah. And then a 4-digit number, let's check it. A 4-digit number, I'm gonna prove that it doesn't work. After trying a few 4-digit numbers, you should have enough intuition to start proving it. So the 4-digit number 9999 has the greatest possible sum of 36. And then the smallest 4-digit number is 1000. And then let's see what would happen if we took 36 times 19. Well, we don't even have to do that. That's definitely less than 40 times 20, which is 800. And that's less than 1000. So the 4-digit numbers won't work. And you can see that the 5-digit numbers and so on won't work either. I'm not going to prove that for now. So let's just use all the 3-digit numbers. The properties of a 3-digit number is that it has 3 digits. So let's make them A, B, and C. It says that the sum of the digits times 19 is equal to the number itself. What is the number itself? So it is 100A plus 10B plus C if you write it out in expanded form. And then the sum of its digits times 19 is just 19A plus 19B plus 19C. So you see 2 equations with 3 variables, so it seems unsolvable. But of course, you're just dealing with digits right here. You can put a restriction on them from 0 to 9. There. Now what do we do? Well, let's see. How about we do something like subtract? Like for example, let's subtract this equation from the top equation. So we'll get, the top expression. So we'll get 81A plus negative 9B, and then plus negative 18C. And that's equal to 0. Why? Because the problem states that this and that are equal. So the difference is 0. I might have made that a bit more complicated than it's supposed to be. Let's just say that like they're equal, so you can subtract them to get a difference of 0. Okay, so we have these. We can actually divide each of the numbers by 9. So we'll get 9A minus B minus 2C is equal to 0. So now we can just do some casework on A. So let's do some casework on A. So first, if A is 0, that can't happen actually, because A is the hundredths digit, and the hundredths digit can't be 0. So A is 1. Let's check that case. Then let's do C first. C could be 0. That means B would be 9. Or C could be 1. That means B would be 7. And then 2, 5, 3, 3, 4, 1. So there are 5 possibilities for those. For A equals 2, let's write that down, 5. For A equals 2, then let's do C again. If C is equal to 1, no, B would be greater than 9. 2, no. 3, no. 4, no. 5, yes. C is 5, then B is 8. C is 6, then B is 6. You can check all of these on your own. C is 8, B is 2. So those are an additional 4 possibilities. And actually, C equals 9, B equals 0 will also work. Yeah, and then after that, let's look at C. Let's look at A equals 3. So then, if C and B were less than 9, then that won't work. Like 9A is 27, and if B and C were less than 9, then this number right here wouldn't be as small as 27, because you'll have to have both 9s for B and C to get this minus 27. So there's only one possibility. Oh yeah, and I should have made this 5 instead of 4. 5 plus 5 plus 1. So we get the answer of 11, and that's it. Problem 4. ABCD is a quadrilateral that is inscribed in the circle O. AB is a diameter. If AD equals 1, CD equals root 2, and BC equals root 5, what is AB? So to make this a bit easier, we can actually use a formula to do it. It's called Ptolemy's theorem. So for a cyclic quadrilateral, ABCD, yeah, that wasn't very good. For a cyclic quadrilateral ABCD, we have AB times CD plus BC times DA equals AC times BD. Okay, that's very confusing. So how I remember it is, first I draw the two opposite lines that are not diagonals, and then I draw these two opposite lines that are also not diagonals. So the product of the blue lines plus the product of the green lines is equal to the product of the diagonals. So the blue and green are all opposite, so that can give you a way to memorize this. This is certainly very useful, especially once you get to like Amy and stuff. So let's think about how we can use this. Let's draw the diagonals because they're an essential part of the theorem. And then we see that they're right angles, like we said in the last solution, in solution 1. So let's set some variables again. This time we can actually be not so careful and set 3 variables: AC equals X, BD equals Y, and BA equals Z. And then we know the other lengths. So Ptolemy's telling us that the product of the opposite plus the product of the other opposite pair of opposite lines is equal to the product of the diagonals. So basically 1 times root 5, which is root 5, and then plus root 2 times z, just say z root 2, and then that's equal to xy. What else do we have? We know by the Pythagorean theorem that Pythagorean theorem on ABC that x squared plus root 5 squared equals z squared. And then by Pythagorean theorem on ABD, we have y squared plus 1 squared equals z squared. So now, how do we do this? Well, let's think about it a little. There's an xy. Yeah, that's hard to get rid of. Xy, that's super hard to get rid of. And then there are those squared terms from the Pythagorean theorem. Let's see how we can use those squared terms. Well, we see an xy and we see x squared and y squared. So can we somehow use that? Turns out we could. How? Question is how? So we want xy and x squared y squared to be multiplied, x squared times y squared, so that we can get this term, and that's equal to xy squared. So the way to do this is to isolate x squared and y squared. So basically subtract 5 and then subtract 1. And then we can multiply these equations to get z squared minus 5 times z squared minus 1 is equal to x squared y squared. And then we can multiply the top equation, the very top equation, by itself or square it. So you can get, I'm gonna do the expanding right now. So 2z squared plus 2z root 10 plus 5 equals x squared y squared. And then it actually turns out you get lucky. Because let's expand this top one. You'll actually find something that can help you quite a lot. So z squared, I mean z to the 4th, minus 6z squared plus 5. That's equal to this, 2z squared plus 2z root 10 plus 5. And when you see in a quartic equation of degree 4, You can cancel out the constant terms. That's super exciting. You can reduce it to a cubic equation by dividing both sides by z. So we'll get z cubed minus 6z equals 2z plus 2 root 10. And then we can rearrange it to get z cubed minus 8z minus 2 root 10 equals 0. So you see, this is the same trick we did with the other equation. You suspect there's gonna be some root 10 in there. So we can do something like z equals, how about a root 10. And then we'll just do this expansion. So a root 10 cubed minus 8a root 10 minus 2 root 10 equals 0. And then let's clear some more space. Then we'll get root 10 cubed is 10 root 10. Actually, maybe I should just do it for you. Now what? This is even uglier than before. No, this isn't uglier than before. Let's divide out all the root 10s. Now this is way better. 10a cubed minus 8a minus 2 equals 0. Or 5a cubed minus 4a minus 1 equals 0. By quick inspection or by rational root theorem, you'll find that a equals 1. So we define z as a root 10, so z equals root 10. So our answer is root 10. Z is exactly root 10. Problem 5. In the array below, how many different paths can you take to spell Berkeley, where each path starts from the top, then goes from one letter to one of the 1 or 2 letters directly below it, step by step, and finally reaches the bottom line? So let's try some. B-E-R-K-E-L-E-Y. B-E-R-K-E-L-E-Y. Okay, so you're starting to get a sense of how this is something like counting paths, right? Maybe. Yeah, maybe you're starting to get a sense of that. So how do we count paths? So the standard problem is go from A to B. And how do we do that? We have to go 3 to the right and 3 down. So this is basically telling us, asking us how many ways are there to go 3 right and 3 down. Permute the letters R, 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 D, 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 in other words. So there are 6 places and there are 3 R's. So let's choose those positions. We can do that. 6 choose 3 equals, I'm gonna do it 20 ways. And then the D's just get placed into the remaining spots. So how can we do something similar like that? What happens? What you should do is that you should make this into a horizontal thing. This thing is kind of slanted. But what you should do is do this. And then you should rotate your head like by about 60, I would say, about 60 degrees to see this. It's still kind of like a parallelogram, but you should like see that it's a bit similar to counting paths. So how do we count paths when the bottom thing is like kind of broken? Well, we can actually split it into two different parts. You'll split it into this and this. So for each part, it's just like counting paths. So you start from B and in the end you go to this Y or this Y, depending on which part you're gonna do it on. So this time each part is a 3 times 4 square rectangle. More like parallelogram actually, but rectangle so that you get the analogy of counting paths. So the rectangle, you have to use 3 downs and 4 rights. So the number of ways you can choose where those 4 rights are 7 choose 4, and that's 35. I'm just gonna calculate it like that. So there are 35 ways to get from this top B to either the left Y or the right Y. So the number of ways to get to either Y is 35 times 2, which is 70. So that's our answer. Problem 6. A, B, C, and D are 4 distinct real numbers such that A plus 1 over B equals B plus 1 over C equals C plus 1 over D equals D plus 1 over A equals X. If X is positive, what is X? Okay, so in these types of problems, what you should do is isolate some variables first and then plug them into some other equations and possibly exploit symmetry since this is symmetric. So let's start with isolating A. In the first equation, A plus 1 over B is equal to X. So A equals X minus 1 over B. And then in the second equation, let's try to isolate C. So B plus 1 over C equals X. So 1 over C equals X minus B, or C equals 1 over X minus B. And now we plug them into the third and fourth equations. So for A, we plug it into the fourth equation to get D plus 1 over X minus 1 over B equals X. And then for C, let's plug it into the third equation to get 1 over X minus B plus 1 over D equals X. So let's simplify each of them. So the top one, D plus 1 over X minus 1 over B. So X minus 1 over B can be changed into XB minus 1 over B. So we have D plus 1 over XB minus 1 over B. But then you can just change that into B over XB minus 1. equals x. And then the bottom one, you can change it into, by adding the fractions, you can change it into d plus x minus b over dx minus bd equals x. Now we just simplified a bit more by removing the fractions, by multiplying both sides by the xb minus 1 for the first equation and dx minus bd for the second. You'll notice that how we derive these equations are actually kind of symmetric. So for the first one, it becomes xbd minus d plus b equals x squared b minus x. And then the second one is d plus x minus b equals x squared d minus xbd. Now we just need to rearrange those equations a bit. So the first one, we can rearrange it into xbd plus b minus d, then plus x equals x squared b. And then for the second one, we can rearrange it into xbd minus b plus d plus x equals x squared d. So now you can probably see the symmetry. Let's take it one step further. Let's subtract the bottom equation from the top one. So we get 2b minus 2d equals bx squared minus dx squared. So 2 times b minus d equals x squared times b minus d. So now you can really see the symmetry. The b minus d's can cancel because, as stated in the problem, b and d must be distinct. So that means x squared is equal to 2. But let's look at the problem again. It says if x is positive. So x has to be the positive square root of 2. So x equals root 2. Problem 7. Joy wants to make number flashcards of all 3-digit numbers. There's only one number on each card. Some cards can represent 2 numbers. For example, if we turn a card with number 198 upside down, we get 861. What is the minimum number of cards needed? So let's look at what happens when we turn each digit upside down. So for 0, we get 0. For 1, we get 1. For 2, it's interesting. If you reverse this, it becomes this. If you rotate it 180 degrees. For 3, it becomes this. For 4, it becomes this. For 5, it becomes this. For 6, it becomes 9. So that's interesting. For 7, it becomes this. For 8, it just goes back to 8. For 9, it actually becomes 6. So we have to find all the numbers that have an actual flipped version. So I just erased all of them that don't. We're left with 0, 1, 6, 8, 9, Let's organize this a bit. 0, 1, 6, 8, 9. 0 becomes 0, 1 becomes 1, 6 becomes 9, 8 becomes 8, 9 becomes 6. Okay. Now, what's our plan? Our plan is to find the total number of 3-digit numbers and then subtract that by the number of cards that can represent 2 numbers. So that's it. That's what we're trying to find. So let's look at how many cards can represent 2 numbers first. So okay, so there's 3 digits. How many ways are there to put the hundreds digit first, let's say? There are 4 ways, because you can't use a 0, but all the other digits are allowed. The tens digit, 5 ways. 0, 1, 6, 8, 9 are fine. And if you turn that upside down, it's also fine. Ones digit. Well, initially you might think that all 5 can be used, but actually if you look at 0, if you turn this upside down, it will become a number that has 0 as its hundreds digit. And we want 3-digit numbers, which can't have 0 as its hundreds digit. So only 4 ways. Yeah, you can confirm that the other numbers still work. So that's equal to 80. Are we done here? No, this problem has a bunch of other loopholes that we need to resolve. So first, let's think of what happens when a number like 101 is turned backwards. It's still 101. Not turned backwards, but I mean like rotated over. It's still 101. That happens with other numbers too. Let's find them all. 101. There's 111. There's 181. And then there is 808, 818, and 888. Those 6. Are we done? No. If you find, like, if you look at something like 609, surprisingly, this thing flipped over is also 609. And there are 619, 689. Then there's 906, 916, and 986. And after like a lot of inspection, you'll find that these are the only ones. 12. So we subtract 12 from this. Are we done? Second, no. No, we're not done. And it's not just that we didn't subtract this from 900, which is the number of 3-digit numbers. We actually didn't account for one more thing. What is that? Reflection. Yeah, just because there are 80 numbers, or 68 now that we subtracted 12, just because there are 68 numbers that can be represented as, that can be flipped to become another different number, that does not mean that 68 cards can represent 2 numbers. It actually means 34, half of that. Why? Because there are 68 numbers and each card can represent 2 numbers. So there can only be 34 cards. So 34. And now we're finally done with all the loopholes and stuff like that. we just have to subtract this from 900. And yes, 900 is the number of 3-digit numbers, which you can confirm quickly. So you'll get 866, and that's our answer.